All right, welcome back. So in part two, we're going to take some of the concepts that we learned about in the previous video on enthalpies of reaction, and we're going to actually apply them to do some calculations of heat energy and amounts of substances. So let's just start right in. So here's the same chemical reaction that we were talking about in the first video, the reaction of hydrogen gas with oxygen to form water. And we established that water is more stable than the reactants. It has a lower potential energy, and therefore when the reaction runs this way, it releases 483.6 kilojoules of energy. Now, one question that we'd like to be able to answer, for example, is this one. How many kilojoules of energy would be released per mole of oxygen gas? And the way we get at that kind of a question is by understanding, how to interpret the chemical reaction. And so if you remember from when we went through stoichiometry, if we interpret this on a mole basis, what this is saying is for every 2 moles of hydrogen that react with 1 mole of oxygen gas, we're going to generate 2 moles of water. Now, on top of that, we have this additional information. What this number tells us is that if you react exactly 2 moles of hydrogen with 1 mole of oxygen, the reaction will release this much energy on the way to producing 2 moles of water. So one way, there are several equivalences that we can establish. One of them is we could say 1 mole of oxygen, when it burns with hydrogen, releases 483.6 kilojoules. Okay, so let me just show you how that would be written. All right, let's try green. So the equivalence that can be written here is 1 mole of oxygen is equivalent to negative 483.6 kilojoules. Sorry, one of my girls is having a temper tantrum upstairs, so I'm sorry if you can hear that. Okay, so this is a key equivalence that we'll make use of. And let's do another example. So for example, let's say the question instead is how many kilojoules of energy are released per mole of hydrogen gas. Okay, well, this is a little slightly trickier. Well, one thing that you can certainly say from just reading the equation is the following. You can say that 2 moles of hydrogen gas, 2 moles of hydrogen gas, when it burns in oxygen, is going to release 483.6 kilojoules of energy. Okay, so that tells us how much energy is going to be released from 2 moles. But the question is asking about how much energy is released per mole. Okay, so that simply, I think you can see if 2 moles releases this much energy, 1 mole of hydrogen is going to release half that much energy. And if you want to calculate this a little bit more formally, what you can do is say, okay, so 1 mole of hydrogen, and then we multiply that by a conversion factor. And the conversion factor is given to us by this equivalence. And so we put energy on top, 483.6 kilojoules, and 2 moles of hydrogen on the bottom. Okay, so again, this is the relationship between energy and the amount of hydrogen that gets burned in the reaction. Okay, 2 moles produces this much. So if you want to know how much 1 mole is going to lead to, then you multiply by this conversion factor. And let's see if I've got that calculated. Nope, I don't. But you can calculate it right along with me. So you just take 483.6 divided by 2, and that gives you 241.8 kilojoules. Okay, All right, so this is, I just want to kind of get your thinking in the mode. We're going to use the coefficients in terms that tell us the mole relationships, and connect that to the energy that is either released or absorbed by the reaction to come up with a conversion factor. All right, let's try another one. Okay, now the way this reaction is written, this is a more typical heat of reaction problem. You're just going to see the chemical reaction, and then to the right you'll see the amount of energy that's either released or absorbed by the reaction as it's written in the equation. So this time you can see that we're taking water and we're doing the decomposition reaction to regain the original hydrogen and oxygen. And so since we're running it that way, then this enthalpy of the reaction is positive. Okay, we're going to go uphill in terms of potential energy. Okay, so the question is, how many kilojoules of energy required to produce 25.9 grams of oxygen gas? Okay, no problem. So we're being asked for kilojoules of energy, so I'm going to start by writing energy. So the energy that would be required is equal to, okay, so we're given a certain amount of oxygen gas, 25.9 grams of oxygen. And now, before we can make use of the mole relationship between the oxygen here and the energy that's going to be required, we have to first get this mass into moles. So it's just a simple mass to moles. You probably knew that was coming. So we're making use of some skills that we've learned. So to convert the mass to moles, we simply divide by the molar mass of molecular oxygen. And now that we have things on a mole basis, now we can use the mole relationship between the oxygen and the energy. So we're trying to find energy, right? So in our conversion factor here, we're going to have to put the amount of kilojoules on the top over the number of moles of oxygen. Okay? And when we chug through all of that, let's see here. We should have, I beg your pardon, I thought I had that, oh, I do have it calculated. Okay, good. When you chug through that, and you should calculate this right along with me, you see that the units cancel out very nicely, moles of oxygen here, so we're going to be left with kilojoules, and that's exactly what we want. And the answer is 391.4 kilojoules. Okay? All right, let me know if you get something different from that tomorrow. Okay, so there's an example. Here's another example. Okay? And if you think you've got it, you can stop the video now and, move on to the homework. But I'm just trying to give you some different looks at these kind of problems. All right, this one is asking, again, how many kilojoules of energy are going to be produced. But this time, it's telling us how much energy is going to be required to produce a certain amount of hydrogen. Okay, so we start this time with the amount of hydrogen. We, just like last time, we got to get that mass into a mole basis. So that's 2.02 grams of hydrogen. And now we are ready to apply the conversion factor that describes the relationship between amount of energy and number of moles of hydrogen formed. Okay, and you can see it's 2 moles of hydrogen is equivalent to 483.6. Okay, so I put the 483.6 kilojoules on the top, and that's 2 moles of hydrogen on the bottom. Okay, and let me see here. This one I don't have calculated, so I'll do that right along with you. So that's 2.75 divided by 2.02 times 483.6 divided by 2 moles. And to this I get 329.2 kilojoules. Okay. All right, so I'll move on. Okay, let's try a totally different chemical reaction. Okay, so you got, in this reaction, ammonia is reacting with oxygen, so it's another combustion reaction to form nitrogen and water. Here's the enthalpy of reaction. First, I would like to ask, is this an exothermic or an endothermic reaction? Okay, the negative sign gives it away. This indicates that it's an exothermic reaction, therefore energy is going to be released. And so which one of these reactants or products would be at a lower potential energy? Well, for an exothermic reaction, if we're releasing energy, then that's kind of like the boulder dropping. And so the products are going to be lower in potential energy, and that's why it's going to release all that heat energy. All right, so how many kilojoules of energy are released per mole of ammonia? I'm just checking my time here. Okay, so you can see, again, it's a pretty straightforward relationship. We're talking about ammonia, so here's ammonia right here, and you can see that there is a 4 mole to 1,530 kilojoule relationship. So we can write that down just to be organized. Okay, so this equivalence is going to form the basis of our conversion factor when we need it. Okay, so it's asking how much energy is released per mole of ammonia. All right, well, so energy equals, per mole means we're asking about 1 mole of ammonia. And now we apply the conversion factor, negative 1530 kilojoules per 4 moles of ammonia. Okay. And to that I get that equals negative 382.5 kilojoules. Okay, so that's how you'd set that up. All right, let's ask a little bit different question. This will be the last one. How many grams of ammonia would be required to produce 274 kilojoules of energy? All right, so this time we're trying to figure out how many grams of ammonia would we need to react with the oxygen if we wanted to produce this specific amount of energy. Okay, no problem. So we start with what we're given, 274 kilojoules. All right, and now again we're going to make use of the relationship between the 4 moles of ammonia and the 1530 kilojoules. So, and by the way, we are trying to this is energy that's going to be produced, so the 274 is strictly speaking, that is a negative number because it's going to be produced or released by the reaction. All right, now we apply the conversion factor, so that's 4 moles of ammonia on top over negative 1530 kilojoules on the bottom. And this will tell us how many moles of ammonia we need, but the question is asking not for moles but for grams. So the last step, we have to multiply that by the molar mass of ammonia, which is 17.04. Okay, and when you work that through, you should get 12.2 grams of ammonia. Okay, so hopefully this is helpful, and best of luck on your homework tonight. Okay, see you tomorrow.